So we are live, yeah. And
Okay.
good evening, everyone, and welcome to the final speaker event of the term. So today's talk comes at a very apt moment. In the fifth week, we actually had a talk by the manager from Climeworks, the company with the first commercial scale direct air capture plant. In that talk, he also discussed how they sequester that captured carbon with an Icelandic partner, CARBFIX, which brings me to our distinguished speaker. Today, we are honored to have speaking to us Professor Oelkers, Professor of Aqueous Geochemistry at the University College London. His research focuses on developing the fundamental geochemical basis for sustainable growth and management of the earth. He was a founding member of the CARBFIX project I mentioned earlier, and currently serves on its scientific advisory board. He'll no doubt tell us more about that project. At the same time, he will share how subsurface mineral storage is a safer and more cost-effective manner of carbon storage. As always, do not hesitate to send in any questions you have via the Facebook or YouTube comment section. With that, I will hand over the time to Professor Oelkers.
Well, great. Thank you very much. And great to be talking to all of you. I've just now learned that you've had a talk now recently with the people from Climeworks. So some of this will already be familiar to you. But since I hadn't prepared that way, I'm going to go through the talk the way it is because I can't change the bits and pieces now. Great. Anyway, right now, as you all know, the world is going through somewhat of a big battle on global warming and carbon dioxide emissions in the atmosphere. On one side, we have, of course, a large number of climate activists, including here Greta Thunberg, and along with the United Nations, suggests that we should be lowering substantially or cutting substantially our carbon emissions. For example, this picture here on my right-hand side shows the potential scenarios proposed by the United Nations to cut down or limit the carbon emissions down to either 600 or 800 gigatons, which is believed to be the limit to keep global warming down to no more than 1.5 or 2 degrees. Now we can see here that each of these suggests that we should be pretty much peaking carbon emissions today and cutting them down to almost zero somewhere between 2035 to 2050. So that's one side of the battle. The other side of the battle comes from many of the people here. And this is actually a group photo of the Oil and Gas Climate Initiative Group, which is a consortium of approximately 15 major oil companies at a meeting that I was attending in Dammam, Saudi Arabia about a year and a half ago now. These are their environmental officers. And they're discussing how to address this. But the collective wisdom of the oil companies, at least as of last year, 2019, showed or predicted that the amount of energy, and particularly hydrocarbons, as we could see here on the figure on our right, is they predict an increase. We see in bars in green oil, red gas, and gray coal, a continuing projection of increasing use of hydrocarbons going forward. So we have this incredible challenge here. On one hand, we've got climate activists, United Nations, and many scientists who are telling us that we need to cut dramatically carbon emissions over the next few years, pretty much peaking them almost immediately in order to avoid climate crises. On the other hand, we've got the petroleum industry coming here and telling us that they project, and this is, oil companies generally aren't evil. These are people who are merely trying to make money. They're beholden to their shareholders, but they predict, or at least predicted as of last year, a very big, a continued increase in carbon use. There's basically only two ways really to resolve this battle. One is for, well, I guess one of these two sides to give in, or somehow to take the carbon dioxide that is being emitted by these hydrocarbons, capture it and removing it from the atmosphere, keeping it from getting in the atmosphere. So as this battle's raged on, at least it looks like for now, the energy companies are beginning to budge and consider what the options are and consider the possibility that carbon emissions are going to need to decrease. And I noticed that when preparing, I guess, a preliminary version of this talk several weeks ago, I started reading the 2020 Energy Outlook by BP, which is one of the industry standards. And I noticed this figure on the right became something like this. And they changed the style of figures a bit. But the important part is here we've got the projections from 2020 upwards towards 2050 of basically the global petroleum consumption looking forward from, again, now from the present into the future over the next 30 years. And we see they've got several different scenarios here, which is the green one is what they call a business as usual scenario. But even this scenario has oil consumption peaking somewhere around 2030 and declining. And they also are considering sort of this net zero scenario in blue, which considers a very, very dramatic decrease by almost a factor of 3 in the use of petroleum moving forward towards 2050. This is a very different projection than just a year ago. So the petroleum companies are beginning to consider that the future may not be more petroleum, more hydrocarbon-based energy going forward. They're hedging their bets a bit. They're not saying that it's all going to go away, but they're beginning to consider this possibility. What's the motivation for this? Well, it comes out on the next slide as one reads further into the Energy Outlook. Is here we've got, and this figure is a bit confusing too, but here we have a plot of the estimated carbon tax or projected potential carbon tax, either as a business as usual in the lower dark and light green curves, or the net zero projection in the upper light and dark green curves. But in each of these cases, in a business as usual scenario, they anticipate that perhaps the best case scenario by 2050, we're looking at a tax of on the order of $50 to emit a ton of carbon dioxide in the atmosphere. And in the net zero, a more drastic potential scenario, they worry about facing upwards of a $200 a ton tax for emitting CO2 to the atmosphere. And note that it takes, as I wrote here down below, it takes about 2.5 barrels of oil to produce, burning that, to get a ton of CO2. And the current market price of oil is about $45 a barrel. So we're talking about somewhere about doubling or to increasing a factor of 5 the real price. And I guess these are prices in inflation adjusted US dollars. So increasing.
Sorry, Eric.
Yes.
We're currently still on the second slide for the screen that you're sharing. Yeah, it's still showing us the second slide. Yeah, sorry about that.
You're still showing the second slide.
Yeah.
How did we do that? Because I'm showing.
Okay, yes, progress now. Yeah, sorry about that.
We'll do it this way then. Okay, I'm sorry about that.
Apologies.
So now I've got the cursor. I will actually, should we start again? Are people watching?
Yep, I think currently there's around 7 viewers.
Okay, well, if that's the case, I apologize for that. We have here the average carbon prices. Again, this is projections for 2 different potential scenarios. One is a business as usual with a carbon tax upwards of about $50 a ton. And the second is a net zero scenario where they project that there's going to be more motivation, there's going to be higher taxes. And anyway, they're looking at anywhere from about doubling to increasing by a factor of 5 based on government policy, the price of petroleum in real dollars, inflation dollars, over the next 30 years, which is the big motivation really for the petroleum industry to consider now lower demand for petroleum products, and also the need to start taking very seriously the need for technologies that will limit the amount of carbon going to the atmosphere. And how one gets there is, at least based on the oil companies' reports, is summarized here. Excuse me. Here is a plot again out of the World Energy Outlook from 2020, The IPCC suggests that we need somewhere between 8 and 18 gigatons of carbon capture and storage. And in their net zero scenario, petroleum companies are at least projecting that the industry will need only on the order of 5 gigatons of carbon storage per year, and also with an input with bioenergy and a bit with afforestation, although the petroleum companies argue that they're not going to be involved in any forestation. And the whole idea of forestation as a way of capturing and storing CO2 is largely losing traction in the scientific world, because people have realized that after a while trees die, and once trees die, they decompose, and you don't really get a net carbon storage from a tree after it's decomposed. So all of this interest in carbon storage has managed to motivate a huge input from the scientific community. Just before I made this, just earlier this afternoon, I typed into Science Direct. Many of you might have used Science Direct, the keywords carbon capture and storage, and out popped 103,160 results. There's been a huge, huge effort by the scientific community to investigate and study all of this, including, apparently, if I look carefully, 1,798 papers published already in 2021, which is quite remarkable since 2021 hasn't even started yet. There's a huge effort to study this and quantify this, and it seems, of course, quite remarkable when you consider the big effort that's been made by the scientific community, how little is actually going on. So there's a big difference between studying something and doing something. The current state of carbon capture and storage is summarized in my next slide, where here we've got pretty much the current state of carbon capture and storage. And I apologize because you see my marks on here because I can't show it piece by piece. But currently, here on this side, we have a plot of the current amount of carbon emissions. Well, as of about 2018, we're looking at 37 billion with a B, tons of CO2 emissions. And this compares to approximately 37 million with an M, tons of carbon capture and storage that are going on worldwide today. So when you put one versus the other, the 17 large-scale, approximately CCS facilities in the world are managing today to only capture and store 0.1% of all the carbon emitted to the atmosphere from all these various different parts of the world. And it's, of course, this sounds pessimistic, but it even gets worse when you consider the fact that a large percentage of these current carbon capture and storage facilities aren't doing pure capture and storage. They're really mostly enhanced oil recovery projects. Now, enhanced oil recovery, and just to summarize this here in the next slide, this is probably not the best slide, but here is, again, to summarize most of the current carbon capture and storage projects in the world are for enhanced oil recovery. Here, of all through 2018, carbon injected to the ground in supposedly carbon capture and storage projects. All this bit in blue is through enhanced oil recovery, and dedicated storage is only these little bits in red. So pretty much almost 90% of all carbon capture and storage to date has been in enhanced oil recovery. And I would contend that enhanced oil recovery is not carbon storage. How does enhanced oil recovery work? Well, I got a little schematic here in my next slide. Here, enhanced oil recovery, what happens is one purchases carbon dioxide, and that carbon dioxide that's purchased tends to be mined from carbon dioxide already in the subsurface. And that's injected with some CO2 that's recycled from petroleum wells, injected into the ground. And what happens is some of the CO2 is stored in pore space, but the goal really is to try to get this injected CO2 to dissolve in the petroleum. When the CO2 dissolves in the petroleum, it becomes more fluid and it flows easier, and you can get more out of your oil wells. So when I worked through and tried to work through the numbers, this is what I came up with. on the carbon storage, the net carbon storage one gets out of that process. And this is really the best I can get from a variety of different sources, and I normalize my EOR math for about 1 million gigatons of injected CO2. Industry-wide, for each 100 megatons of CO2 injected, typically about 68 of those megatons are mined CO2. In other words, that's not CO2 that's captured, it's actually coming out of the ground. It wasn't in the atmosphere to start out with. 32 of the megatons are captured primarily from the oil you get out from the enhanced oil recovery. And you get out about half of the CO2 you come out with dissolved in the oil. And actually what happens is when it comes out in the oil, it actually bubbles out of the oil. It's just like soda pop CO2. And you get an additional 88 megatons of CO2 coming out from burning the new oil that you've gotten out. So when I do the calculations, for every 100 megatons of CO2 you put in, you get about 138 megatons of CO2 out. My argument is I would argue this is not carbon capture and storage. It's actually producing more CO2 than it's emitting. So if we go back to the previous slide, and if you remove enhanced oil recovery from the picture, we get more like 3.7 million tons of CO2s being captured and stored in carbon storage, direct carbon storage projects worldwide, compared to the 37 or so billion tons being emitted. So right now we've got only about 0.01% of all carbon being emitted to the atmosphere being captured and stored. This has got to be increased hugely before we can make any sort of dent in the limit, any sort of dent in this 37 billion tons of CO2 being emitted to the atmosphere today. Now, because of the huge scale and the huge amount of space that we need to put all this carbon dioxide somewhere, the need to do this, most efforts on carbon capture and storage are aiming at somehow taking that carbon dioxide from some source, whether it be direct air capture or whether it be from a point source like a factory, and injecting it into the subsurface. And there's two basic approaches towards geologic carbon storage. The first, which I guess many would argue is more conventional carbon storage, takes pure carbon dioxide and injects it into sedimentary rocks where it will stay as a relatively buoyant CO2 gas bubble in the subsurface for many years, typically hundreds of thousands or millions of years. An approach that we've been working on for the last 15 years in the CARBFIX projects involves taking our carbon dioxide, dissolving it in water, either on the surface or as we inject, and injecting it into reactive rocks like basalt to try to provoke the chemical reactions between the carbon dioxide and the reactive rocks to make stable carbonate minerals, notably things like limestone. Many of the buildings on your campus are made of limestone. This is a calcium carbonate mineral. One of the big advantages of this approach for subsurface mineral storage is it can be cheaper, but it's also far safer and more secure than the conventional type of carbon storage. And I just want to emphasize that a bit with the aid of my next slide. This is somewhat of a classic picture of classic CO2 storage in sedimentary rocks. One injects carbon dioxide into the ground. It remains a separate gas phase for many years. Eventually, it starts getting trapped in small pore spaces, or it dissolves over time. And even these numbers here are a little bit vague and arm wavy here. And over many thousands, 10,000s, or millions of years, eventually it may react chemically and be fixed as solids in the subsurface. In the approach that we're taking by injecting CO2 as a dissolved phase into reactive rocks, we get instantaneous solubility trapping. It dissolves in the water very quickly. And this is an important point because CO2 in a separate phase, whether it's structurally trapped or trapped in pore spaces, is still buoyant and wants to come up out of the surface and come back into the air. It's only once it dissolves into water that CO2 is less buoyant. It's denser than the other water. It tends to go down instead of up. And mineral trapping, the carbon dioxide will rest in place for millions and millions of years. Much of the motivation for this sort of approach comes from nature itself, as I'll try to summarize with the global carbon cycle with the next slide. This is a schematic illustration of the global carbon cycle, and unfortunately it's a little bit gunked up, this figure, because it is, I'm not able to show it directly with my PowerPoint presentation, but carbon dioxide comes out of the air. It comes out of the earth typically through volcanoes, where it will increase the concentration of CO2 in the atmosphere. But the major process that takes CO2 out of the atmosphere is its dissolution into rainwater as it rains, which makes a mild carbonic acid. This carbonic acid rains on the continents, where it reacts with silicate minerals through a process called weathering, which dissolves particularly the calcium and other divalent metals that are in the carbonates, and makes carbon dioxide and makes free calcium plus carbonate, which eventually go in the ocean. And let's see if I move this here, eventually moves in the ocean and reacts in the ocean, produces alkalinity to make calcite, and some CO2 is given back. But over time, this process has pretty much cleansed the atmosphere from CO2 over geologic time and has kept global temperature relatively well buffered. Just to summarize this in 3 quick reaction steps, mineral carbonation does the same thing. We dissolve CO2 in water, which makes a carbonic acid. The carbonic acid promotes the dissolution of silicate rocks. For example, here, I wrote this reaction with a silicate mineral. In this case, it's diopside, which releases calcium, magnesium, as well as silica to the atmosphere, to the water. And then these calcium reacts with the bicarbonate and makes calcium carbonate or magnesium carbonate minerals, which are stable minerals. One big advantage of this process is that it's chemically spontaneous. For example, the reaction of anorthite, which is a calcium plagioclase, one of the most predominant minerals on the surface and the crust of the earth, reacts at 10 bars of CO2 with water at 25 degrees and makes calcite, calcium carbonate, plus clay. And it results, actually, it's thermodynamically favorable. It produces, it's exothermic by a bit more than 15 kilocalories per mole. So this is actually energetically downhill. Anorthite plus CO2 wants to make calcite and wants to make clay and carbonate minerals out of it. It wants to fix the CO2. This is what the world does naturally. Similarly, if you prefer green rocks, you could take fosterite, which is this olivine, add to it 10 bars of CO2, and spontaneously, in fact, creating energy, one will make magnesite and amorphous silica out of this directly. This is chemically spontaneous. This is what these minerals like to be doing in the presence of CO2 and some water. It happens, of course, on the surface of the planet all by itself. I've got 2 examples here. First, this is a piece of basalt that I picked up actually on a field trip last year in Saudi Arabia. All of this white material here is calcite that formed from the carbon dioxide dissolved in rainwater, reacting with this piece of fresh basalt on the surface of Saudi Arabia. Alternatively, deeper in the earth, I've got a second example. This is me here pointing out a big piece of basalt near the town of Albany on the South Australian coast. And all these white veins are calcite that's precipitated due to chemical reactions between this basalt in the cracks and fissures as CO2-rich waters flow through basalt. This is exactly analogous to what we're doing in Iceland today. Once the CO2 is there, fixed as carbonate minerals, it stays for a long time. For example, and this is rather a much nicer slide if I could show it to you through PowerPoint, which I don't think I can, but consideration of the global carbon cycles shows that the average residence time of calcite in the crust of the earth is about 190 million years. So once calcite goes into the crust, that's where it pretty much wants to stay for very, very extended periods of time. So taking advantage of this and taking into account of the need to capture and store CO2, there have been 3 pilot projects to date worldwide exploring this and using this. The first is CARBFIX 1, which was our pilot we ran in 2001, where approximately 200 tons of fresh water dissolved in carbon dioxide was mineralized in fresh basalts in Iceland at a depth of 500 meters at a temperature about 30 degrees. We upscaled this in 2014, initially with about 12,000 tons of CO2 a year being captured in fresh water. We injected into the ground at a depth of 1,200 meters at a temperature of 250 degrees. And approximately we see somewhere about 80% of this carbonated in 3 months or so. And there are also one additional test, which was done in Willow, Washington, somewhere around 2012 as well, where 1,000 tons of pure CO2 was injected into basalts as a pure CO2, and they observed the mineralization of this CO2, but they weren't really able to quantify in detail how much occurred. I'll present just a couple of details about CARBFIX 2, the ongoing projects going now. Here with the aid of our next slide. CARBFIX 2, this is a picture of our power plant of the Hellisheiði in Hellisheiði, Iceland, which is located about 30 kilometers inland from Reykjavik. Reykjavik Energy, which I think now is called On Power, injects about 25 million tons of geothermal fluid into the ground each year. And we're now taking carbon dioxide, capturing carbon dioxide in water, along with hydrogen sulfide gas. And we've been injecting it continuously into this downhole stream since 2014. The capture plant right now looks something like this. This is our capture plant, and it's a very simple process. It's inspired directly from nature. This is our capture plant. This is about a 20-meter tall tower. We've got a couple of our engineers down here for scale. CO2 and, the exhaust gas from the power plant is injected at a pressure of about 6 bars into the bottom of this scrubbing tower. And into the top, we have a shower of pure water. And inside of this scrubbing tower, we've got a whole bunch of little polystyrene beads to help mix the gas and the water. And by the time the gas goes through the tower and the water comes back down the other side, the water's pretty much reached equilibrium with the gas. And it's captured, I think we've optimized it. Currently, it captures about 80% of the carbon dioxide directly from the exhaust gas, and the insoluble gases then vented to the atmosphere. This water charged with CO2 is then transported without being depressurized, because depressurizes the CO2 comes out just like it would in my can of Coke Zero right here. Keep it pressurized, and we inject into the subsurface. We'll just go right here. And this is where the injection system, you might have seen this slide perhaps a couple weeks ago if somebody gave you a summary of CARBFIX recently. The CO2 and gas charged water comes in to the injection well, where it's mixed with the geothermal brine and injected into the subsurface. It looks pretty much like this. It's a bit noisy when you go into this little hut to do this, but it's actually welcome to do this because the geothermal brine is fairly warm. This is Iceland. It can be rather cold and nasty outside. Anyway, this CO2 enriched water then gets injected into the ground and along this path down to a depth of anywhere between 800 and 2,000 meters, where it then flows over time to a series of three, we'll call it monitoring wells, between 1 and 2.5 kilometers further downstream. And there we're able to sample these wells to verify the fate of the injected CO2 and also hydrogen sulfide, which we're injecting as well, gets captured along with the carbon dioxide, which is a very good thing because this actually, the alternative is, well, currently the laws in Iceland are preventing the emissions of hydrogen sulfide, and the alternative to capture hydrogen sulfide is a reduction process, which is fairly expensive to do, which costs, just give it things ahead, it costs somewhere about $300 to $500 a ton to capture hydrogen sulfide gas. And through this process, along with CO2, we're doing this for about $25 a ton, which saves a huge amount of money for the industry. Anyway, we take the samples here, we bring to the hut, and this is Deirdre Clark, one of our now former PhD students, who did our sampling for us and chemically characterized the fluids in the subsurface. And from the characterization of the fluids in the subsurface, as shown here, we can determine the amount of dissolved sulfur that we measured in the output versus what we can predict if from a series of chemical tracers we inject in the ground would be there if there was no mineralization of the injected gas. And we determined here pretty much all of the sulfur and more than 50% of the CO2 injected has been fixed as minerals within 2 to 4 months of injection. So the process is fast, it's efficient, and basically to summarize what we know about carbonation, this process of turning CO2 into rock is that it takes weeks to months in the laboratory. It took us about 1 to 2 years at 30 degrees in the CARBFIX 1 project, and the ongoing project here in 2 to 4 months at the CARBFIX 2 project at a higher temperature, we get somewhere around 50 to 70% of our CO2 fixed over time. Coming back to the cost, and this is a very important issue, the current cost of CARBFIX right now is summarized here. It's about $25 a ton of CO2 and or hydrogen sulfide captured and stored. Most of the cost is actually in the capture, which about half of this $21 a ton capture was for the amortized cost of creating the capture plant. Half is the energy needed to do that capture. The transport's about $1 a ton, the injection costs about $1 a ton, and the monitoring about $1 a ton. This is about $25 a ton, which is fairly cheap. This is approximately the cost of, right now, the price of CO2 emissions on the European Carbon Trade Scheme, which makes it actually financially interesting. In addition, the financial motor to this CARBFIX for years now has been the relative low cost of capturing and storing hydrogen sulfide, as the power plant's not allowed to emit hydrogen sulfide to the atmosphere, though they are actually allowed to emit CO2 currently. We also considered the price of doing this same approach in other places. Carbon capture and storage on site in Iceland is about $25 a ton, where energy is relatively cheap and we already had the wells drilled. If we include the drilling of the well, and if we include the average energy price worldwide, we're still at about $50 a ton for capturing storage CO2 with this approach. So in summary, it's an efficient and safe approach for capturing and storing CO2. And we're in the process of trying to move this and adopt this approach in other places and at larger scales. The opportunity for capturing and storage CO2 this way is fairly great. And we can make estimates of what storage capacity is by considering natural analogs that are available. For example, we looked at how much carbon is naturally stored in reactive basaltic rocks in Iceland. And here we've got a schematic view of the amount of carbon dioxide stored as a function of depth in two different areas, cross-sections in the Reykjanes Peninsula in Iceland. And we find from about 50 to 100 kilograms per meter cubed of CO2 is stored as calcite through water, basalt, CO2 interaction naturally in these reactive basaltic rocks. And a big advantage is these reactive basaltic rocks are all over the world, as shown in the next slide. Here I've got just a schematic, well, it's actually a picture of the world here. Here in purple is shown all of where these reactive basaltic rocks are, all over, mostly spread out on the continents, and here in various parts of the ocean. And here in orange is the relatively young part of the ocean floor, which contains fairly reactive basalts. As we can see here, there's large amounts of potential targets, reactive rock targets, where we could adopt this project and this approach throughout the world. And some of the biggest sites on land are emphasized here. The biggest is actually in the rift zone in Ethiopia. Anyway, the point is these are located in many different parts of the world, and the potential storage capacity by our estimation is huge, as shown in this table here. The largest, again, in Ethiopia. We estimate that the potential carbon dioxide storage capacity is anywhere from 15,000 to 40,000 gigatons of CO2 per year. This upper figure 1,000 times more than the annual carbon emissions worldwide today. So one other place, for example, in the Arabian Peninsula, where I'm doing a fair bit of work, we have upwards of, 4 to 10,000 gigatons of storage. And in Iceland, where we're working, there's, again, we estimate 2 to 5,000 gigatons of storage. Again, this is enough to store decades worth of global carbon emissions. So the potential is there. To summarize what we know about carbon capture and storage, mineral storage, the technology for carbon mineralization by injection of CO2 dissolved water into reactive basaltic rocks is ready, it goes. And this is actually a core that we've gotten out of our site in Iceland, where we see here the calcite that was precipitated from one of our injections. It's cost efficient. It has a number of advantages. It's being more safe. It limits long-term liability. So it can be applied most anywhere throughout the world where there are reactive rocks. And as I showed earlier, these sites are all over the world. So the potential is there for widespread application. And I don't have to go through a great deal about this, but one of the ways we are looking at moving forward right now, because you've seen some of this earlier, is combining CARBFIX with direct air capture. And we're expanding that now, as you've probably heard. Just so I go very rapidly through this, the air capture units being produced by Climeworks look something like this. They're relatively small. The CO2 goes in, gets captured by a set of filters, and the CO2 comes out. Next, this is one of the tours that we took with some of our students and collaborators to visit the unit. And as you've probably seen before, this captured the CO2 by sucking in air. There's big fans here. It captures on a chemically bound filter, and then they close up the doors here use waste heat from the power plant, and the CO2 comes off of these filters. And we are now injecting this into our subsurface along with the CO2 we're capturing from the power plant. And as you probably also heard, Climeworks, and this is one of several ways of combining air capture with, using air capture. Climeworks is just one of several ways of air capture. And we're combining it now with our carbon mineral storage. And the beauty of this is it decouples the location of where we store carbon dioxide from where the carbon dioxide is produced. As a result, we could stick carbon storage sites anywhere in the world where it's convenient, which allows us to use mineral storage, which we believe is a safe and potentially cheaper alternative for carbon storage, pretty much where the rocks are more favorable and where where people and society and with the local society and local community is in support of this. So to summarize the current state of carbon capture and storage here, first of all, right now it's rather pessimistic. There are relatively few carbon storage projects active in the world, and the need for upscale is going to be absolutely huge, whether you take either the projections of the petroleum industry or you take the projections of the United Nations and the climate activists. It is encouraging that the petroleum companies are beginning to embrace carbon capture and storage. I know myself, I'm working with several petroleum companies today trying to upscale mineral carbon storage to other sites around the world. It's also changed dramatically the directions of many petroleum companies who are, well, let's say, reconsidering some of their personnel and some of their priorities going forward. But as I mentioned earlier, in total, no more than 40 million tons of CO2 are being captured and stored today out of the somewhere around 40 billion tons are being stored emitted. So we need a huge amount of upscale going forward over the next 20 years to get anywhere near the sort of projections of the UN climate goals that we have, which for many people and many of you that are considering careers, this is a huge opportunity going forward because this is going to be potentially a huge industry going forward. As I just glossed over very briefly, direct air capture is feasible. It may be necessary for the global climate goals because something I didn't mention is that more than half of the CO2 going in the atmosphere today, including things like air travel and heating, residential heating, is dispersed sources. So air capture is probably going to be a necessity. It also allows us to capture and store CO2 where it's best on the earth to do it. So the technology is available, but the big problem right now is that a financial model is lacking. It may come. It may be that those projections of carbon tax are going to occur, and there will be a carbon tax that will oblige industry and the public to limit CO2 emissions and make it financially interesting to do carbon capture and storage. And I would say that that's not actually an unreasonable thing. I leave at the very end here that a little bit of math. It takes burning approximately 330 liters of gasoline to create 1 ton of CO2. So merely a 33p tax per liter of gasoline would give 100 pounds of funds towards the storage of each ton of CO2, which is more than enough money to pay for most CCS efforts going on in the world today. So, and I should mention that, in fact, all of us are paying more than 33p per liter tax if you look at your typical gas bill. Right now, it's far in excess of this. So the public is probably amenable to pay that level of tax per liter on gasoline. and it would go a long way towards solving the global need to start limiting carbon emissions. So thank you very much for bearing with me on this rather technologically limited talk, and I'm welcome to your questions.
So thanks a lot, Professor Oelkers,
Sure.
for that very insightful talk. Especially the part on the very affordable cost, the multiple locations around the world as possible, as well as the decoupling using direct air capture. Those were really very insightful stuff. So we actually have a few questions already from the audience. So maybe the first one would be from Anlin. So the first is from Anlin. So she asks whether regulations would actually have to be required to kind of restrict or prevent enhanced oil recovery from happening, as well as what is kind of the most effective way of promoting, in her words, kind of real carbon storage.
There's nothing really wrong with enhanced oil recovery. I mean, it does get more oil, and the world wants and needs energy. I don't think there's any problem with it. It is possible. I mean, there's several points. One is enhanced oil recovery has been a financial motor to learn a fair bit about how to do carbon capture and storage. Without it, the petroleum industry wouldn't be injecting CO2 in the ground. In order to inject CO2 in the ground, you need big infrastructure. They've learned quite a lot from it. And so there's nothing wrong with it. We just have to be better about capturing the CO2 or from the oil that's produced from EOR to keep that CO2 from going in the atmosphere. Some of it, as we should know, and many of you would know also, is that one of the technologies being championed for this energy transformation is hydrogen as fuel for many things like running airplanes and things like that. Projections are almost half the hydrogen that's going to be used in the future is going to come from petroleum. You take petroleum, you then chemically separate the hydrogen from the carbon. You then capture a pure CO2 stream, and you've got to store that pure CO2 stream somewhere. So it's the oil itself isn't evil. The question is, can we use it in a way that doesn't increase carbon dioxide in the atmosphere? The most effective way to promote real carbon storage, the problem is financial. It's all a financial thing. If the financial motor is there, it'll get done. I've talked to many in the industry, and they say, give us money to do it, and we'll do it. Well, of course, it's either a matter of giving them money or not. And I should say, there is a question who pays. I guess many climate activists would say the petroleum companies should pay, but the petroleum companies will just pass on the cost to the public anyway. A number of years ago, I had lunch with, well, I'm not going to name names, but I had lunch with one of the technological officers for a major oil company. It was a very nice lunch. It was somewhere in France, and we were talking about carbon capture and storage and who should pay. And he looked at me and said, Eric, we don't burn the CO2. We just sell it. If you want, you could just fill your swimming pool with it, and that's fine. We're not forcing you to burn it. It should be the public that pays. The public's going to pay one way or the other. The answer is the public's got to decide that they want that this is a priority. Government's going to have to tax it somehow, make a cost on it, and it will promote carbon capture and storage. The bottom line is it's all financial.
And I guess on the same point of kind of financial incentive, the next question also kind of talks about it. Yeah. So he was asking.
And remember, it wasn't until the petroleum companies started predicting that there was going to be a tax of $50 to $200 that they started projecting oil. But again, the petroleum companies aren't evil. The petroleum companies are merely addressing a demand. And everyone who doesn't, hey, I'm heating my house. It's hydrocarbons. I take airplanes. It's hydrocarbons. I'd be a hypocrite and many of you would be hypocrites as well if, you say that we shouldn't use them. We just have to, like everything else in the world, whether it be hydrocarbons, whether it be plastics. We have to pay for taking it out of the ground. We have to pay for the disposal as well. We just haven't been doing it.
Mhm. Yeah. So I guess on this same issue, so Tom was asking how would so I think you had this slide that actually showed this
$25
per
a ton
Yeah.
is the price of capturing and storing. One of the things that we do, and we developed on all of this, is we basically capture the CO2 by dissolving it in water. It's very cheap. Basically, it's not rocket science. In fact, the world captures CO2 all by itself in water. If you take a glass, it's not glass, but if you took a glass and you filled it with distilled water, it'll have a pH of 7. You take that glass of water and you put it on your table, and you let it sit there for about 4 hours. You put your pH electrode back in, it will have a pH of about 5.8. Why? Because the CO2 in the atmosphere is already dissolved in and equilibrated with the water. You could take that CO2, pour it into the ground, and it will, in the right rocks, it'll carbonate. It's just not a very efficient process. To make that process a bit more efficient, you pressurize the water, and you pressurize the CO2, and you do it at a higher pressure. And as you increase the pressure of the gas, you get more CO2 going in the water. It's just Henry's law. It's just, and the point is, that's a relatively cheap process. So the efficiency of that sort of process, of course, depends on the concentration of the carbon dioxide. Where air capture gets more expensive, and that's, I think our people in Climeworks would tell you it's a much expensive process, is you're taking carbon dioxide out of the atmosphere, and so you have to use more energy to get CO2 more concentrated out of the atmosphere. But the $25 that we're doing includes the capture, the storage, it's everything. It's because dissolving CO2 in water is cheap.
Mm-hmm. And
the challenge
question
the reason you won't do that for the atmosphere is you don't get that much water into the atmosphere, that much CO2 into the water. You'd need just huge amounts of water. You need oceans of water. So when you have something as dilute as the atmosphere, you have to do other processes, or else you just need too much water. Sorry.
Okay, yeah, sorry for interrupting. Yeah, so this third question by Jessica. So she was asking, what is the significance of CARB2 actually being implemented near a geothermal plant? So does this technology require the need to be connected to a carbon-emitting plant? Yeah, electricity.
The answer is it doesn't have to be. The reason it is near the geothermal plant is largely, well, it's historic to a large degree. CARBFIX, we started in 2009, and actually was the president of Iceland at the time, who 2 years before he provoked the global financial crisis, put us together with Reykjavik Energy and asked us to come up with a solution. And the reason they needed a solution was, actually, it's to be relatively brief, Iceland can produce a huge amount of geothermal and hydroelectric energy, but they have difficulty exporting it. So what they do is they import raw aluminum ore. They smelt aluminum ore in Iceland to make aluminum and ship that out. That process produces carbon dioxide, and they embarrassingly had among the highest per capita CO2 emissions in the world. And we were put together with Reykjavik Energy to come up with a solution. And the reason it's there is that's where they already had the drill holes. That's where they already had the engineering, the pipelines, everything else. It was just cheaper to do there. Plus, they also have all of these wells already drilled, so we could easily monitor what happened in the subsurface. It was just easy and convenient. I mean, we're scientists, mostly academic scientists. We work on a very low budget. We had to take advantage of the infrastructure that was already there. But I would say that, though, of course, I can't say where because I've signed more non-disclosure agreements than I could ever imagine. But we've got several sites around the world now that petroleum companies are looking at, and they're sometimes in the middle of deserts, some are next to desalination plants, some are next to power plants. They're in various different places. So they're all over. But it's like everything else, as academics, you always go to the places where it's cheapest to do the demonstration.
I can imagine. Yeah. So on this related question of location, we have this question by Charlotte on kind of the location of this potential CO2 storage locations. I think you had this presentation on like where the locations are. Yeah. So does it change kind of in terms of problems and benefits when it comes to oceanic storage?
We're working on the
continents.
We're working on the continents. Well, a large amount of CO2 storage locations are now beneath the ocean. The biggest European project right now is Northern Lights. They're offshore. They're offshore Norway, and the UK consortia led by BP and Total have a similar one going on in the North Sea in the UK sector. And these are going to be fairly large projects. They're offshore. The global potential for storage on the ocean is huge. The problem is it's really expensive to do. These offshore projects you're increasing the cost of drilling, you're increasing the cost of transport tremendously. So they are going forward largely in Europe because nobody wants to inject carbon dioxide on the continents anywhere near where people live. This may be overcome by mineral storage because once you store CO2 as a mineral, it's not coming back up. We are exploring right now submarine storage, but our plan is, and our current projects are actually working on the shore and using directioned wells to sort of inject the CO2 into the subsea floor from the coast. And again, that saves huge amounts of money. The other advantage of doing this below the ocean is we could use ocean water to capture CO2. And that's a big plus because we use fresh water currently for capturing CO2, and fresh water is a commodity in many parts of the world. So So we're aiming at that right now, and it's part of the future, but we're going to have to optimize all this technology more on the continents where it's cheaper to do for now.
And do you have a rough ballpark figure of how much more expensive it is? I guess compared to the $25 per ton that has been raised for your
factor 10 to 20.
Okay.
Those are expensive. That infrastructure is very expensive.
And we have this next question by Tom. He was asking what's the energetic cost of pushing the CO2 down?
It's another advantage. That's another big advantage of mineral storage. Yes. The answer is, it's quite interesting. I actually didn't know. This is a good question. When you inject pure CO2 in the ground, it takes energy. Why? CO2 is more buoyant than water. You actually have to push it in. When you dissolve CO2 in water, it's heavier. CO2 charged water is heavier. It pours in by gravity. It just pours right in. It's like, here it is, demonstration. It just goes downhill. So the answer is none. It takes no energy to do it at all. It just pours in. It's going downhill. So that's easy. It saves a little bit of energy. Pure CO2, you got to squeeze in.
Maybe just a quick question from myself. So previously you talked about the high cost of direct air capture. So do you think it would actually be a cheaper method if instead you capture the CO2 from a fossil fuel power plant and you actually have a transport system to all the sites that you actually showed us just now? How do you think cost? costs would actually change.
It is cheaper. It's always the cost of capturing CO2 goes up is inverse to the concentration of the CO2. Just thermodynamics. It's just basic thermodynamics. So you need more energy. The more, excuse me, the more dilute your source, the more expensive it's going to be. Can't do anything about it. So the point is, people start, carbon capture and storage will start largely with point sources. Carbon capture will start largely with point sources. But the point is, it's not going to solve the problem. Somewhere a bit more than 50% of all carbon emissions are from dispersed sources. To get anywhere near where climate scientists say we need to be by 2050, we're going to have to capture air capture as well. But there are clever ways of using waste energy, like waste heat, to your advantage, which is what Climeworks does. They use waste heat from the geothermal power plant, and they also have, you've probably seen pictures. They've got one of their carbon capture units on top of a incinerator plant in Switzerland. They do that. So, but it takes energy. That's the bottom line. People they'll get clever to do it. They'll try to use different processes to capture. And there's others. We could go on for a couple hours on different technologies on air capture. But it's, again, the bottom line is the more dilute the source, the more energy it takes. You could be clever about where you get the energy from, but it still takes more energy.
Okay. And the transport costs in terms of having it at a different location, that would be minute as compared to this capture cost?
I would have to go work through the numbers. Transport costs are not insignificant. We have designed a carbon hub for Iceland, and it's competitive, I would say. We're talking tens of dollars, tens of pounds a ton to ship carbon dioxide from mainland Europe to Iceland, for example. Mm-hmm. And they're talking about doing that anyway. So they're not Iceland, they're talking about shipping CO2 from France to a hub in the UK. So, I mean, we're talking about tens of dollars a ton. It's competitive.
Okay.
And the other point is, about cost. It's very dependent on your site. It's very dependent on all sorts of little bits and pieces. Cost depends on where you get your energy from. It's very difficult to translate cost from one place to another.
Mm-hmm. And just a follow-up question from Tom. So previously he was asking about the energetic cost. So he asked, but you have to compress it before then, right? Which kind of takes energy. I guess he's talking about the CO2.
When we capture CO2 in water, we compress the CO2 and we compress the water. Well, we pressurize them. And then after they're pressurized, we just stick it in a hole in the ground. The pressure is used to increase the solubility of the CO2 in water. You could take CO2, you could take water, equilibrate it with CO2 in the atmosphere and pour it down the hole, and it'll carbonate. That example of piece of basalt that I picked up off of the ground in Saudi Arabia, it's carbonating right on the Earth's surface. It's that very process. But to do that, to any sort of efficiency, you need a huge amount of water. So to cut down the amount of water, you pressurize the amount of water you pressurize the CO2 in the water to get more CO2 into the water, and then you inject that in. It's not necessary, but it limits the amount of water we need to use. And that's very much an engineering decision. I mean, optimizing the amount of water, the amount of CO2, the energy used to pressurize, and all of this. One optimizes that.
Okay. Yeah. And just another question for myself. So kind of just reading a few research papers, quite a few also talk about surface mineralization. So kind of like making use of mining tailpipes. Have you heard of that? Yeah. So how does kind of the subsurface mineralization compare to that in terms of cost, capacity?
One of the tricks that happened was two things on there. First of all, it's fine. It works. It's a good thing to do. Second is you don't get gigaton scale storage area from it. You'll get megatons, but every bit helps. It's not as simple. One, it does it all by itself. Mine waste carbonates all by itself, just like, again, that piece of rock that I showed you. The challenge there is actually optimizing it. What happens is many of these carbonation reactions are volume positive. And so what tends to happen is that you react the outer bits of these waste piles. You then clog up the pore space, and subsequent water falls on it and flows right off the top and doesn't get into these waste piles. But what people are doing now is putting holes into it, poking holes into it so the water can get in. It works. It's cheap and it should be done. And you'll get megaton scale. You'll get megaton scales over time doing it. It's not going to save. It's not going to be the gigaton scales, that we're going to need to address global systems, but it should be done.
Okay. Yeah, thanks for that.
Basically, it's going to be contributions of everything. And when people are being paid $50 to $100 to $200 a ton to do it, it's going to happen.
They will do it.
I'm in contact with a company that's buying up mine waste all over the world for just this very purpose. And they're getting it cheap. They're just trying to make sure they get a market for it. That's what they're busy right now trying to find a market for it. But people are doing it.
Yeah. And that seems to be all the questions that I have, as well as the audience.
Great.
Yeah, so once again, I would like to thank you, Professor Eric Oelkers, for coming on today. It was a really insightful talk.
Sorry about the technical challenges. Iceland, I would recommend
you.
Because I find that to be a little bit easier to give a more proper performance. Well, thank you all. I hope you all have a great evening. It's dinner time here, so I'm going to go have some.
Same to you. Good evening. Yeah, see you.